This is the front sheet and advice on how to complete the questions. I thought I'd put that up. So you've got a 3-hour exam. It's running with 10 minutes reading time, and you're not allowed to have calculators, books, or anything else except your brain. Right, so there are 4 questions. You need to do all 4 questions, and you can do working on the opposite side. Don't write in red like I've done here. Okay, so what I've done is just summarise what's covered in each question. Not particularly helpful really, but some people like to see this. So question 1 is very easy, I would suggest. It's about scheduling and utilisation and some general concepts. So if you've done the labs, you will find this pretty straightforward, hopefully. Question 2 is the arbitration bus systems work. So you will be expected to understand some arbitration logic and the constraints around arbiters and how they operate and when they don't operate correctly. And we'll talk about that today. So the other questions are, question 3 is on real-time operating system implementation, kernel functions, so the use of semaphores, synchronization primitives, and event flags, and sleep, processor state, that sort of thing, and how they're implemented. So you should be able to describe basic functions, not detailed code of course, but you may have to explain some code if it's fairly general, and talk about the performance of these functions. Do they scale in a linear or quadratic or constant execution time, for example? And there is also some questions on synchronization. Okay. Question 4 is about real-time system design. So you've done a lot of that. You've done the pendulum lab and you've worked through implementation and different alternative design strategies. So that will include testing as well. How do you test these systems effectively? And fixed point representation and rounding. Okay, so yeah, that's basically all of the subject really, unless I've left something out. Alright, so what I thought we'd do today is look at the 2013 paper that's similar. Now the syllabus was different. There's a few things that are different which I'll point out as we go. The main difference is there's no data acquisition systems discussion in 5881. There was in this unit. And yeah, there was less on synchronization as well. But anyway, we'll come to that. Right, so what I thought I'd do is just run through these questions with you and maybe discuss what you think about them in terms of how you'd answer them. So I will reveal the answers after we've talked about each question. I think that's probably more useful to you guys, so you can come up with ideas. So when you're designing a real-time system, you've done a lot of this sort of stuff. You've got to break down the problem into different tasks that are concurrent in their structure. And they have different priorities. So how do you actually do this? What are the objectives in this process and what constrains you? So you might have a particular algorithm. It can be expressed in a parallel set of tasks, possibly. So how do you choose the tasks and their priorities. What's the general idea there? So you're faced with a problem. How do you actually break that down into these tasks? So what are the constraints first? Yep. All right. Yep. So how does that relate to priorities then?
So,
Yeah. So they apply to processes that are independent, really, and periodic. So that's a simplification, I guess. But you can model a lot of things approximately in that form. So if something operates very frequently, you give that a high priority. Yeah, it's actually not the execution time, it's the frequency of the deadlines that we've learnt is the critical thing in that. So what are the other things you'd like to do? So one strategy is every little thing you need to do, you would create a new task for that operation. So how would you think about that? How would you critique that strategy? So there might be 100 things you want to do, and you've got 100 tasks. Is that a good solution?
No.
Why not? Yeah, so some things you could lump together in one task and then save the overhead of context switching, presumably. So how would you lump those together? Yeah, similar frequency, yeah, or the same frequency, in fact, the same timing, pretty much. So things that need to be done at the same time, you would do together, obviously. Yeah, so the main objective is to minimise the number of tasks, because that simplifies the problem, but the tasks should have similar timing. So here's the list that I came up with. You might think of other things. So high repetition rates you'd give higher priority, and you want to maximise the independence of your tasks with respect to data and timing. So if they're different timings, then you would, of course, separate them. So the other thing you do is you try and identify common functions in the software that you can reuse, but that doesn't relate to the timing necessarily. So the primary objective here is to simplify your design process and make it easily maintainable. So you want to separate things into functional units, but also timing is considered in that process. So that's a very general sort of question. Yeah. So you will be given hints on how much to write by the space given in the exam. So there's half a page for that. Or more, actually. Here we go. So let's have a look at this guy. Can you read that down the bottom? Is that fine? Yep. Okay, mutual exclusion between tasks and interrupt service routines. Common problem. Firstly, why do you want to exclude tasks from simultaneous access? What's the reasoning there? Why do you need mutual exclusion at all? Because that would slow things down, of course. It's like having a single lane road and you've got all this traffic trying to go through it.
Accessing a shared resource. So you're going to changing it.
Yep, so if you want to print something, then you only want one task printing at any one time. Yep. So what's another example? Of a shared resource, yeah. Different shared resource.
Memory?
Yeah, memory. So what's the issue there?
With one task is using memory and then another takes over. So the task that was interrupted will then write over when it gets control of the again.
Yeah. Another way of saying that is you get an inconsistent view of a memory data structure. So it might be a whole list of different parts of a collective or a data structure. So you need to maintain consistency, and then mutual exclusion will allow that to happen. Yeah. The other case that we looked at was where you increment a variable in two different tasks. And the process of incrementing is not atomic. In other words, it splits into several actions. One is to load from memory into a register. The next one is to increment that register and then to write back to the memory. So there's three things there that if you interleave two increments into those three parts but interleave those actions, you get an inconsistent result. And we looked at an example of that. Okay, so if you are implementing mutual exclusion, how do you do that in a real-time system? What are the methods? Semaphore, yep. So tell us about a semaphore. What do you do? Yeah, which one? Choose. No. Oh yeah, okay. You need to initialize it to 1, the semaphore, because the first task needs to enter the critical section. If you initialize it to 0, no one can enter the critical section, ever. No, you have a pen first, yeah. Yeah, so a critical section, you need to wait for a semaphore, and then you post after you exit. Yeah, so obviously you need to initialize to 1, yeah, in that structure. What's another way of doing it? Yeah, you can use event flags, yes. Yeah. What about disabling the scheduler? Okay, so you can turn off the scheduler, okay? You can stop context switching for a short time. That can be very effective. So what's the difference between disabling the scheduler and, say, using a semaphore in this critical section? There is a big difference. What is it?
Will the semaphore just stop a particular task from going ahead?
Yes.
But it can still be interrupted by another priority task.
That's right. So in a critical section, you may have another task that's not involved in that critical section that wants to run. And if you disable a scheduler, that can't happen. But with semaphores, you can make it specific to that code, and it's only 2 tasks that enter that particular code that are then scheduled sequentially, effectively. Okay, what about interrupt service routines? You can't use a semaphore in an interrupt service routine, because if you block an interrupt service routine, the whole operating system can come to a grinding halt, because interrupts need to be processed. So how do you do that? All right, you need to disable interrupts. Okay. So in an interrupt service routine, you need to do this because there's no other way of blocking. So this prevents other interrupts coming along and interleaving in your critical section. There are other mechanisms, hardware mechanisms for multiprocessor systems where you have shared memory. So you can have an indivisible test and set operation that can interleave multiple processors on a hardware bus, for example. So these can be used as synchronization across many different cores or threads that are parallel. Okay, so that's pretty straightforward, hopefully. Oops, I want to show you the answer. Okay, can semaphores be used within an ISR? Well, the answer is yes. You're shaking your head, but the answer is yes. You can post, yeah. You did this in the pendulum lab, didn't you? So you were thinking of the previous question, fair enough. Yeah. Okay, if yes, there are there restrictions. Yes, there are. What are they? Can't pen, you can only post, yeah. Okay. All right, that's pretty obvious. Page down, come on. Right, so this question is on event flags. All right, so do you remember what an event flag can do? So it depends on the word size. So they store events within a word. It might be a 16-bit word in your particular processor, so you can then have 16 different events encoded in that event flag. And these events can operate concurrently. I mean, they can be independent of one another. So the event flag can then, you can post to an event flag. So if you have an event, you can say that particular bit, that event, which you have a bit mask for, is then set or cleared, depending on what you want to do. And you can also wait on an event flag. So when you're waiting on an event flag, what are the options? So you've got this group of bits that represent multiple events, and you're waiting on those events. So what are the alternatives? So when you wait on an event flag, it can block you as a task. So it puts you to sleep, well, in a block state. So what are the alternative methods? Do you remember?
Like different logical.
Yeah, yes.
So it's like an and or.
Yeah, so if you're doing and, what happens? What's
Wait for all of them.
you got to wait for every event to be set or cleared. You can choose either. Okay, what's the useful one in terms of synchronization? So in a semaphore context, you can wait for two events. So you just pend on two semaphores. Pend on semaphore A, then you pend on semaphore B. So if the two events arrive, A and B, then you get through those two pens, and that's fine. You've then successfully waited on two events. Okay, so what can an event flag do that semaphores cannot do? Yes. So if you wait for two events, you want them both to have occurred, then the semaphores can do that. But if you're waiting for two events where either of them is enough for you then to proceed, then semaphores will not do the job. Why not? Yeah, so you have to depend on semaphore A maybe first and then B, but if A does not occur but B does, you never get through that code, okay? So that's why event flags are particularly useful. So you can do an OR, which is the one we're just talking about, which allows you to choose any one of the events as a way of unblocking. All right, so that's something you need to remember. Now, in the pendulum lab, you probably didn't have that level of complexity, so you didn't need to use event flags. Not sure if anyone did, but you don't have to. Okay, what functions in a real-time kernel does the timer interrupt, allow to be implemented? Okay, so the sleep function's the obvious one. And timeouts. Okay, so the timeouts, if you wait on a semaphore, you can list a timeout as a parameter, and if that time is exceeded, you then return from that call without being blocked any further. And you get an error code to tell you that you have timed out. All right, so can you answer the next question? If you want a task to delay itself for no less than one timer tick, what call should you make? Why 2 when we want 1?
Because could call that right before a timer interrupt.
Yes.
So that section can be less than.
That's right. So, yeah, as you point out, if you call it just before the timer interrupt arrives, then it will return almost immediately with a count of 1. So you need 2 to guarantee at least 1. Yeah. So that's good. And you'll see the timing diagrams in the notes that illustrate the variability when you have a higher priority task that can run in preference to the one that's calling the sleep, then it can actually delay it for an indefinite time. Okay, so that could last, the sleep could last as long as the higher priority task needs to run. And the other thing you want to do is measure time with the timer ticks. So that's the call that you've used OS time get in the pendulum lab, presumably. So they're the general questions. So, all right. So question 2 was about dynamic memory in a real-time system. Now this question was a little bit confusing because some people thought this meant dynamic memory as in the difference between static and dynamic memory. But the question is not about that, it's about malloc. But we realised this and we gave people the benefit of the doubt because the question was ambiguous, all right? Even though it's talking about the kernel. But anyway, so with dynamic memory in a C context, you have the heap, which is a whole collection of memory, and you can allocate memory from that heap and then deallocate it. But the problem is that of fragmentation, so you get the memory starts to break up into regions that are allocated and unallocated in a random way effectively. And if you want a big block of contiguous memory, you may not be able to do that without reshuffling all of the memory. So in a real-time kernel, they actually solve that problem by having blocks of memory that are quite large, and they allocate those, and you need to say beforehand what size memory blocks you use and how many are pre-allocated. So it does restrict things a little bit. Okay, so the real-time kernel provides the source code for the product. Now this is not always the case, so there are lots of real-time kernels out there that provide the executable effectively without the source code. So why do they do that? So why does Micrium, that's the micro COS2 company, why do they provide full open source? Yeah, it actually helps them because people can see any bugs, but also it's about reconfiguring the system to use less memory and less functions that you don't require. So that os config.h allows you to turn off, say, if you're not using event flags, you can turn off the code and memory usage associated with that. So that's about saving ROM, read-only memory. And the other thing is you can specify a different maximum number of tasks, event blocks and so on, which saves RAM memory. So there is this OS task change prior that you used in one of the labs that had a bug in it that you could actually fix. So you fixed that bug in the lab yourselves. The other advantage is we can understand the operation of the real-time kernel at any level you wish to follow. You can actually see how it works at a very detailed level. The disadvantage, of course, is IP protection. Intellectual property is all out there, and your competitors could copy your neat ideas without too much trouble. They'd have to hide it in some way, but if you're only supplying the executable, you could hide that. So there are the issues around that. Right, let's just... So this question is about the ready table that you see here. So we've got the OS ready table, this guy here, and you've got the OS ready group, which is a summary of that table, and then you've got the task priority down here. So suppose priorities 0, 4, 19 and 63 are ready to run. What values are stored in these data structures? Okay, can you answer that? I think we need to write here, so I'm going to have to... I'll get there eventually. All right, so here we are. Doesn't really work out. Okay, so do you want to have a go at this problem, or do you want to just see the answer? So 0, 4, 19 and 63. So what's the entry in the OS ready group? Can anyone tell me what you'd expect to see there? I've got the wrong thing.
Another one for each row that has one of those. It's set.
Yeah, so you'll have...
2 and 7.
Yeah, 0, 2 and 7 is correct. So you'll have a 1 in 0, 2 and 7 and zeros elsewhere, and of course you'll have 1s in those positions in this table as well. So that's the answer, and you can do that. So you can see that here is 0x85 in hexadecimal, and then table entries 0, 2 and 7 have non-zero values. Okay, so that's pretty straightforward. So the question is how to use that information. So if we want to remove a task from the ready list, how would you do that? So what values result from removing priority 19 from the ready list? Okay, so you just have to make 19 a 0, this guy, which you can do with this code. Okay, so you'll remember that, you probably don't remember, but you've got these x and y components, and the priority shifted right 3 bits is the index into this array here, so it's the value down this side here. So you can call that the y value, and the x value is the lower 3 bits. So you've got x and y. Okay, you've got x across here, which is the lower 3 bits of the priority, and y is the upper 3 bits of the 6-bit priority. And the y value will determine the bit in the group, and the x value the position across the byte in the ready table. Okay, so if you want to remove a value, you can just AND it with a 0 in the right position, so that's why there's a not in front of this OS map table. The map table, you remember, takes a number and generates the bit shifted version of a 1 in that bit position corresponding to that number. So it's a way of then clearing the bit corresponding to the x value, which you see here, because you're ANDing with the bit mask of the lower 3 bits, so that extracts the x value. You then get the bit position of that, and you then clear that. And if that result is 0, so if you've cleared the particular byte here, you've cleared a bit which is the last bit that was a 1, it will then result in that being a 0, and then you can remove the group corresponding bit as well. Okay, so that's pretty straightforward. Now you don't have to actually write that code in your answer. It said pseudocode here, so you can just explain it in words if you wish. In the exam you'll get full marks for that. So I don't expect you to memorize this code, you just have to understand how it works. So how do you find the highest priority ready task? Well, that's critical in an operating system to get the scheduler to pick out the highest priority ready task. So you have to unmap. You've got to have a mapping from a set of bits in a byte that picks out the highest priority or the most left one in that byte. So that's what this table does. If you look at the notes, it maps 256 possibilities of a byte to the bit which is the highest priority and the most leftmost bit in that array, and spits out the number corresponding to that bit. So that's just a single memory lookup table function. So that's done here with y from the ready group. So you pick out the group with the highest priority, and within that group you then pick out the highest priority x value across in that position. So in other words, you pick out the highest priority bit in this group, and if it was bit 6, you then go to that entry in the array and you pick out the highest priority across there, which is the x value. And that then gives you the highest priority ready task. Okay, so this question is a hard question, question 2.4. Now you remember we discussed this synchronization function where you have n tasks arriving and they want to synchronize through the calling of this function sync. So this question is about that problem. So that we implemented that with semaphores and event flags in the lectures, you might remember. But this question is asking people to write a kernel call, OS sync, that uses the internal structures of the operating system to do this. And the advantage of doing that is you can do this much more efficiently. So the way we'd operate this is you'd initialize this with an OS sync create n, where you denote the number of tasks you want to synchronize, and it remembers that. And then later on, when you have different tasks calling, they call OS sync, and the kernel then waits for n of those calls from different tasks, and then the nth one will unlock the other n-1 tasks. So that can be done quite effectively within the operating system because you have access to the ready table and other data structures within the operating system. So you should be able to write this code, and it turns out that it should have constant execution time as well, which is quite different to the code that we looked at in lectures. So here is the way you do this. You need to store 2 integer variables. The value n that we set up has to be stored, and the number of calls that are in progress. We need to keep track of that as well. So once the number of calls equals n, then we release the other tasks. So you can set up a list of blocked tasks in the same way that we just looked at in that ready table. So we call this an OS sync table. So you use exactly the same structure. And you might remember that when we discussed semaphores and other synchronization primitives, they use this same data structure within the operating system to record blocked tasks on a semaphore, for example. That's stored in that same structure of that table with the X and Y components. So this is a sketch of the code. So you can create the particular synchronization primitives by using a pool of OS events like we do with the semaphore, and you then have two integer fields that you set up with n and 0 for the current calls. And then you have this table that you initialize all to 0. So that table is going to record the priorities of the tasks that are blocked on this synchronization call. Okay, so here is the implementation of OS sync. So you come in, you check if the pointer's 0, then you've got no initialized value there. So that means you need to exit with an error. So you enter a critical section of the operating system because we're starting to play with variables that are shared in the operating system. So we increment the number of tasks that have called this, and we check if it's equal to n. If it's less than n, you just return by issuing a scheduler call. So you block the current task, and at the end you call the scheduler. So if you have reached n, then you of course zero the number of current calls, and then you go through and make tasks ready to run. So that's just through the ready table structure. So you've got a list of priorities that are blocked, so you then make them ready to run in the ready table. You just do the corresponding bits. So that can be done with an OR operation, and then you clear the sync table of all the sync tasks. So it's just a matter of housekeeping, really, in that sense. So that implementation will run very efficiently. So as I said, this is a tough question. It's only worth 5 marks. But surprisingly, a lot of people got it right, as good as you'd expect in exam conditions. This solution here is much more detailed than you'd actually have time to provide, and I'm aware of that. So, yeah, it's just the concepts that we're looking for. All right, so arbitration logic. This is a question about time-bounded asynchronous arbiters. So if you have a time bound on an arbitration circuit, so you're trying to resolve who is the first request, that needs to be done with a flip-flop internally, effectively. So you're susceptible to metastable failure. If you bound the time, then you can end up with a indecisive output. So this is the synchronous arbiter failure. We went through that in lectures. I don't think we need to do that again, but just briefly, there's 2 scenarios that have 2 different outcomes. The scenario where request 1 wins is number 1. Number 2 is where, sorry, that's wrong. Request 0 wins in scenario 1 and request 1 wins in scenario 2. And between those 2 scenarios, you can have a continuum of events. So you can slide one into the other. That's one way of doing that. And you'll end up with a crossover point where there's the metastable output. Any questions on that? No? All right, so here is the tree arbiter that we looked at in lectures, and this appeared in the exam. So you remember you got this mutual exclusion element. The first request coming in will be asserted on the output, and this delays the response until a decision is made. And once you have one of these two asserted, then it relays that request up the chain to the next level. And this logic here just takes care of the handshaking, as we'll see. So that request then gets resolved. If the top half is first, then you get an acknowledge coming back, acknowledge 0, 1. If the bottom half, of course, is first, then that would go through to the bottom half. So you get one of these two acknowledge signals coming back as a 1, which then triggers the appropriate acknowledge going back down the chain. So these Muller C elements, do you remember how they work? Well, it tells you here. So the output equals the inputs when all the inputs are equal. Okay, so it's waiting for two ones. It's like an AND gate, but the AND gate doesn't reset until the two inputs are 0, both zeros. Okay, so you get a 1 coming back, and if it happened to be that request 0 is the winner of the ME, then that acknowledge would be asserted. And that can only drop when request 0 drops via this path around there. Okay, so there's a timing diagram to complete on the next page. But before we do that, can you tell me what conditions can this arbiter enter a metastable state, and what are the consequences? Do you know what we're looking for there? Can you give me some examples? There are 3 examples you should be able to think of here. Can you think of one? Yep, so yep, so these two arrive together, or these two here arrive together. Yep. Yes. So the third example is where these two requests arrive together. So either or of these, they don't have to be metastable, but if these blocks arrive together, then this guy can go metastable. So there's 3 mutual exclusion elements here. There's 1, 2, 3. So they're the 3 cases that you need to think of. So that's what's listed there. So in all cases, the outputs are delayed until the state settles, so there's no problem in terms of the output. So these circuits we discussed in lectures for the ME will automatically wait for the metastable state to separate in terms of the 2 outputs. Okay, so the timing diagram is listed here. We have requests 0, 1, 2 and 3 operating in that order. So maybe I'll just go back. If you can remember that, we can discuss quickly what happens. So request 0 arrives before 1, so therefore 0 is given the ME output in this node, and then you get a request issued at the top level before the bottom one has activated, and therefore acknowledge 0 will come out first. And you then have request 1 asserted and request 2 and 3. So acknowledge 0 will be asserted, then request drops, okay, and that results in this request dropping here, and this one, R23, is still active. So then you get an acknowledge on 23 coming back. Okay, so let's look at the timing diagram. So request 0 results in 0, 1 as we saw, and acknowledge 0 gets the first acknowledge. Now what happens next is this order of arrival is 0, 1, 2, 3. So 1 should be next if it was a first come, first served resolution. But you see that 2 gets the acknowledged next because of that tree structure. So you remember the bottom half was then enabled second. So you can see that it has to then resolve between the 2 and 3, and 2 arrived before 3, so that's resolved locally, and you get an acknowledged 2 coming out. So when that guy drops, then the top half gets priority, and acknowledge 1 comes out. And when that drops, finally acknowledge 3 comes out. So this is an example where the order of request is not respected in the acknowledgement in this arbitration circuit. I think it was you, Sean, that asked me, can that happen in the lecture? So here's your proof that it can happen in the exam question, just where you want it. Okay, we're running a bit short of time, so we'll just skip through these a bit quicker now. So this is a first come, first served arbiter. You remember that you can resolve in pairs the order of arrival. So these 3 MEs resolve 3 input requests, 0 before 1, 1 before 0, that's the coding. And the problem then is you get 8 combinations here, but only 6 of them correspond to valid orderings. The other 2 correspond to circular requests. So 0 before 1, 1 before 2, and 2 before 0 can occur in a circular pattern. And that needs to be resolved by this logic, and that's what's done down here. So you can check the details of that, but it needs to acknowledge the fact that that can happen. So all combinations of these MEs need to be covered in your unique allocation of acknowledges. Okay, so you can check that later. Okay, we've done this example already in previous lectures on fixed point rounding of an expression, so you can look back at that. And finally, this is the last question that's relevant to us. So custom instructions, we discussed those in the lectures. For a NEOS, why would you bother? Give an example, and the example in this case, you could actually make a PID loop instruction given an error and bunch of constants you've stored. So this is a way of speeding up a particular operation that occurs frequently in your design. All right, so you can ignore the data acquisition questions. Okay, so those of people that arrived late, I did, where is it? I did explain the coverage of your exam. So you have a 3-hour exam, 4 questions, and here are the questions, what's covered in each of the questions. So I think we better stop there, but you can read through that anyway. If you've got any questions yourselves, please ask. We've got 3 minutes nominally. Yeah.
Are you recording the lecture?
Am I recording this lecture? Yes, I am. Yes. Yeah. I will, if you email me, I will make an appointment to see you if you have questions. So that's something. I think your exam's quite late in the exam period, so you're probably not focused on this stuff at the moment. But towards the end, make an appointment and come see me if you have questions, and we'll go through that. All right. There are tutorial-style questions on the web page that you can go through as revision, in addition to past exam paper questions. All right, so we'll better stop since there's people waiting. All right, so do get your reports in by 11 p.m.